Well, thank you very much, David, for that kind introduction, and also for organising the forum today, and to everybody else for taking the time to come and listen to the presentations that we're putting on. I'd just like to start really with some individual or some personal remarks, picking up on a theme that Evan mentioned, and that is the fact that UK really is a marine province. You know, if you talk about oil and gas to somebody who's not in the business in the UK, the first thing that comes into their mind is probably an offshore oil platform. Whereas if you go to Texas and you say, I'm in the oil and gas business, the first thing they think about is probably a nodding donkey, a beam pump somewhere up in Oklahoma pumping oil that it's probably been doing for the last 90 years. Even within that setting, though, within the UK, it's really interesting to note that a lot of the innovations within onshore seismic have actually come or originated in the UK. There have been a number of drivers for that, and I think it's probably interesting just to drill down a little bit more and to see that within the UK, Scotland has actually been particularly prolific in the ideas. And I guess the next speaker is Ian Jack, who probably not that you'd know from his accent, but actually was educated at Glenarmond School in Perthshire, and is a graduate of St Andrews University. So I think his Scottish credentials are quite strong. And if you drill down a little bit more into that, into the surname of Jack, there's actually a small town called Och on the Black Isle, just north of Inverness, where your surname is either Patient or Jack. So I don't know why Ian got the Jack rather than the Patience, but there we are. So in the mid-1990s, Ian was very instrumental in trying to push onshore seismic away from these massive cabled systems towards much smaller, more portable systems that were just easier and cheaper to use. So that was an initiative he put forward. Concept Systems, based in Edinburgh, looked at an idea but didn't take it forwards. But they've subsequently gone on to do a lot on the software side. And personally, I was a co-founder of a company called VibTech that developed a system called the Unite system, which was sold to Sercel in 2006. And that is probably one of the more successful cable-free companies or cable-free systems that's on the market at the moment. I'm now with Wireless Seismic, and I'm the Director of International Business Development, so I'm actually the only entity outside the Americas for Wireless Seismic. Having joined Wireless Seismic, there's just another issue that I'll just touch upon. It's probably a topic for another day, David, is that of funding. And the thing that really struck me about Wireless Seismic compared to VibTech was the level of funding that they were able to get in the United States. They were able to raise 3 times the amount of money that we did at VibTech in half the time. And I think that is something that UK PLC needs to address within the oil industry in order for us to drive innovation forwards. Anyway, I'll get on off my soapbox and get on with the formal presentation. So I've called this, I should just go back. I've called this presentation Promises Delivered because, as David indicated, we've been here twice before talking about what we're going to do. And in the last year, we've made massive steps forwards to actually making the system a commercial reality. So in terms of background to the system, and I'm sorry if you've heard this before, but I think it's worth going over again for those of you who haven't been here before. The company was incorporated in 2006, and our head office is in Sugar Land in Texas. We are the developer of the RT, that stands for Realtime System 2, which is actually our second generation fully scalable wireless seismic system. And the whole tenet of the system is that the seismic data is transmitted from the box to the central unit and recorded in real time. The company is funded by Chesapeake Energy and Energy Ventures, and we currently have more than 70 full-time employees. The first commercial delivery was in February 2011, and we now have 6 customers worldwide in USA, in India, with our customer there is about to do a survey actually in Indonesia, in China, and in Colombia. And I think what speaks volumes as well is that we believe we're about to get some repeat business, so we haven't managed to put the clients off. So let's start by reviewing the systems that are in common use at the moment. So typically, out in the world of seismic, cabled seismic networks have been there for a long time. They do a good job, but they have certain drawbacks. They're difficult to transport, they're difficult to deploy, they're labor intensive, you can be HSE challenged. They're also difficult to maintain. A single cable break can be very disruptive and can actually stop your acquisition, and they're costly to repair. Indeed, some oil companies will tell you that you should budget up to $200 per connector on a cable per year just to keep that cable transmitting your data. So that's a very, very expensive P&L expense that doesn't always come out on the balance sheet. Another aspect of cable systems is their complexity, and the complexity is becoming a barrier to larger channel count deployments. In some cases, the systems don't function well in rough terrain, and they're not always acceptable in some environments, such as urban. You can see this picture on the left here, trying to run these cables across roads and things does give you a bit of a headache, especially if you're in very highly urbanized area. Cable systems are also inflexible for varying receiver intervals. And if you're a seismic contractor working for different oil companies, you can't always guarantee that you're going to have a 25-meter group interval. Sometimes it might be 75 meters. So when you're buying your seismic system, you need to scale it for the biggest receiver interval that you're going to encounter, and then just coil up the cable and carry it around with you for all those 25-meter interval jobs. So one thing we haven't mentioned as well is the fact that animals just absolutely love to eat seismic cables. Now, those hawk-eyed amongst you will see that that's a string of geophones, but I think the principle remains. So the obvious conclusion is that we need a better solution to our seismic surveys, our seismic systems. So let's have a look at cableless versus cabled systems. So there are two primary types of cableless systems. Nodal, which for the purposes of this talk I'll define as systems that basically sit there, record data, write it to a hard drive, and give you only a very limited amount, if any, QC data back. So you're basically shooting blind. And at the flip side to that are wireless systems, which can give you either a degree of QC data, or in the case of wireless seismic, the entire data set back within the shot cycle. So this is an example of a wireless seismic system. Each of those stacks is 500 channels. So what you see there is 1,500 channels of RT System 2, which if you were to have a cable equivalent, you'd probably need 2 or 3 trucks to put that lot in. So what are the issues with nodal systems? Well, you physically have to collect the seismic data. So this is the Unite, sorry, wrong button. This is the Unite system. Reasonably well qualified to comment on that one, given that I was one of the inventors of it, and I also gave it its name. Basically, you take this data harvester, and then you have to come close to the units to download the data, which is fine, it works very well, but it's labor intensive, and you don't get the data in real time. With Unite, it is possible to get the data back in real time, but it uses a cellular configuration, and it's very hard to get all of the channels to send all of the data back all of the time. Another way that you can harvest your data with a nodal system is by basically taking it back to your truck somewhere, hooking it up to a machine and sucking the data out of it. And in some systems, you recharge it at the same time. After you've done that with these systems, you then have to get your very expensive and complex data transcriber to take the data from its format within the box to put it down into a usable SEG format. All of that takes time. So you've got limited QC control during your acquisition, and you can't view your data at all while you're recording, so you've got no idea what your noise specs are or how many of your units are working when you're out there. And our clients tell us, and this is something that they don't tell you in the brochure, is that you need 10 to 15% redundancy for download and recharging. So basically doing what this guy's doing here. So for a 10,000 channel system, you're tying up between $1 and $1.5 million worth of capital for just downloading your data. And that's something that people don't very often factor into their into their calculations for how much the cost of use is going to be for the system. So the conclusion is that nodes overcome a major limitation of cabled systems, but they introduce several new ones. So what's all this about wireless? Well, the challenge with wireless and introducing it into the business is to make the networks robust, self-sustaining, and transparent to the user. So why is real-time wireless technology just starting to penetrate the seismic acquisition market? So there are various technical and operational challenges. So historically, there have been limitations in the radio technology. The radio system has been very complex with multiple jumps trying to get the data back to the central unit. And also power management and battery life has historically been a really big issue. So at Wireless Seismic, we've been focused for a number of years on overcoming these challenges. And the result is that since 2011, we've had our systems out there in the field, and we've proven that if you can engineer the system right, basically you can get a radio system out there that is highly commercially viable and scalable. So what are the traditional issues with wireless systems? Well, the first issue is the radio transmission range and the complexity of those radio systems. And the solution is basically a novel radio protocol and a simple architecture for the system. So historically, if you can imagine that on this little schematic on the left here is a receiver line, which you can see in a real picture here on the right-hand side. So historically, with the wireless systems that we've had, this unit out here would have to send to the collection unit in one hop. We'd have a different way of doing it. We break the whole thing down into one small hop. So each receiver acts as both an acquisition unit and a relay station. So basically we transmit the data long distances, but over very, very short hops. Also, we've developed our own very robust proprietary protocol. It's not Wi-Fi, it's something we developed ourselves with Wi-Fi, TCP/IP type protocols. Bill Gates put in lots of overhead there. That basically means a much smaller proportion of your total bandwidth is available for transmitting data. So we've got around that by doing our own protocol. So these receiver lines then come down into what we call line interface units that collect the data, collection points, and these can handle multiple receiver lines, or subnets as we call them. So the backhaul radios transmit the collected data back to the central unit, either using 5.8 gigahertz radio connection like that, and that mast is very man-portable, and you can stick it up in 10 minutes. Or, once you get to this little box that you can see on the ground here, the output from that is actually TCP/IP, so you can put a simple Ethernet cable into it, you can hook it up to a 3G cell phone coverage if you like, or you can put just a straight VPN tunnel on. So a second issue with traditionally associated with wireless systems is limited battery life and the duty cycle of those batteries. So I don't know if you can read this slide. Oh, that's interesting. Don't know how that happened. Unfortunately, I'm a Mac user, so this has rather translated. But I can tell you what this says. So basically what we did, we posed 4 different questions to respondents in the test, in the survey. And we had battery life of 3 days, 7 days, 14 days, 21 days, 4 weeks, and 8 weeks. And we asked them whether or not they felt this amount of duty cycle would be sufficient. So basically the purple that you see on the right-hand side there was where people said that a 3-day duty cycle was simply not enough. By the time we got to 4 days, the majority of people were saying, well, actually, 4-day duty cycle is sufficient. But we found that the sweet spot was between 14 and 21 days, that by the time we got to 14 days, only 4% of people were saying that 14 days was not sufficient duty cycle. By the time we got to 21, everybody was happy that that was enough. And in fact, the majority of people were saying that was too much. So we concluded from that the sweet spot was between 14 and 21 days. So we built our system and engineered it that it would be able to do that. So power management within the system is a primary criteria for for the engineering and the build of the system. So we put a lot of time into minimizing the power consumption of our unit, and we've had it independently verified by Verify that the average consumption of our unit over a 12-hour cycle is 360 milliwatts, which is the lowest power consumption of any cabled or uncabled unit there is out there. And we've done some clever things to enable that. For example, when you deploy the unit, we use GPS to make its location, but as soon as the unit is hooked up and deployed onto the line, the GPS turns off, and then we keep our timing discipline from the line interface unit. GPS is a really power-consumptive piece of equipment, so getting rid of that really decreases the power budget. So batteries must maximize the availability of power. So we have two built-in lithium-ion they're built-in, integral, but detachable lithium-ion batteries with very, very high power density. The battery life is within the range of 14 to 21 days, and typically we find in the field, despite the 14 to 21 day specification, the batteries last between 15 and 25 days. And it's possible to put higher capacity batteries on if you really want to extend it out to 40 days. The battery chargers, well, they need to be lightweight and portable. And our batteries that you can see on the side of the unit here, and here, they have all of the charging circuitry actually on the battery themselves. So the result is that our battery chargers are very inexpensive, and they're simple, and they take up a very small footprint. So this unit that you see here, that's sufficient to charge 80 batteries from flat in 8 hours. So you can charge 120 channels worth of batteries on one of these units in a 24-hour cycle. I was on a field crew in Kansas. That sounds a bit like a punishment, really, but that was just last week. And that was an RT System 2 crew with 2,500 channels, and they only had 2 of these units to handle that number of batteries. So the result is that a wireless-based system can now be deployed that meets the market requirements for efficient and effective power management. So let's have a look at the architecture of the system. We believe our system is basically a drop-in replacement for a cabled system. So we don't think of it particularly as a nodal system or a cable-free system. We think of it as a cable system without any cables. And that's very much as how the architecture is designed, to have these receiver lines that come into a subnet down here, and then you can either send the data through a fiber optic cable or through the 5.8 gigahertz radio link. So the complete system is very simple. There are only 3 types of hardware units that you need to make the system work. The first is the wireless remote units, or WRUs, which are these things here. We have the line interface units that handle each of the subnets, and then we have a central unit that records the data. So data is delivered to the central system in real time, which means that you've got a real-time noise monitor, you've got constant QC, you don't need to physically go out onto the line and collect the data, and we basically do this through our high-capacity radio network. So, as I just said, data is delivered to the central unit in real time. And in the middle of 2012, we field tested 10,000 live channels in the field, and we got data back in real time. So deployment of the system is very simple. And I was going to say, until my little hiccup with my previous slide, that we are the Apple of seismic systems compared to everybody else who's working with Microsoft. But I think that's maybe not the best thing to say now. But anyway, the deployment of the systems really is very simple. You just take the unit and you tilt it up like that, and the unit starts to come on. You put it down, and it goes through a self-test, and that's it, basically deployed. That's all you have to do. So even I can do it. The whole idea is to try and alleviate the potential for operator errors. Once it's deployed, it performs its own self-tests, checks its location, and then connects to the wireless array. So this is what we call a process of dynamic line formation. So that really does reduce the operator errors and greatly enhances the deployment efficiency. The system automatically recognizes a repeater in the line formation, that is one of these units that doesn't have a set of geophones attached to it, and the units will automatically add themselves to the end of the line as they're deployed. So again, no operator action is required for that. And it's possible, and we'll just go back a couple of slides, to insert a snake. So for example, if you've got a no permit zone here, you can stop the subnet at that point. So this would be the live subnet here to this line interface unit. You can then insert a couple of repeaters. So then you can make this subnet actually part of this receiver line. So this line interface unit here is handling all of these receivers round to there. So you can be very flexible with the way that the system's deployed. So both the wireless remote units and the line interface units automatically transmit their status back to the central. And you might be looking at this thing here and wondering what that is. Well, that is what we call a Fracstar, which is used by one of our clients, Seismic. And the RT system too is absolutely ideal for surface passive monitoring because there are no cables running around. So it's very difficult for a system like Unite to work in real time on this because it's very difficult to put a cellular configuration into these spokes because the distances are really quite large. This might be 1,200 channels in one of these legs. That's I think about the biggest number they've used. So although we use the system in conventional seismic, we're seeing very significant application within microseismic. So the telemetry has the ability to skip heal. So by that we mean, for example, if this unit here for any reason goes down, the system will automatically put in a skip and will just basically zero that trace there and allow the transmission to continue. The data in there isn't lost; it's stored in the disk. On the memory of the unit until the telemetry is restored. The system uses automated power leveling. Again, that's another thing to basically decrease the amount of power consumption in the unit. And that's especially important in complex areas like this, where there's a lot of cross paths and so forth, where things may vary. Somebody moves those bins, so suddenly you've got a different power requirement for the unit. So all the time we're looking to reduce to the minimum the amount of radio transmission power. We also have automated transmission retries. So you've got a road crossing here. Well, this would be very difficult with a cabled system. You'd have to find some way to get the data to the other side of the road, be it with some kind of protection for the cable, or put it up overhead, or use some kind of complex microwave link. Basically, we can just put our units down. If there is a block like that large truck coming along, it'll just retry and the data will get through. We also have a comprehensive suite of QC tools, so the observer can view and analyze the radio links and the performance of the system in real time, all of the time. We have a new feature called Rapid Fire, which basically enables us to packetize data in the unit for up to 10 minutes worth of data. We're currently making a vastly bigger buffer within the units, but that's what we've got at the moment. So the thing is, the acquisition is actually decoupled from the data collection. So that gives us zero overhead between shots. And it means that acquisition can continue when the telemetry is oversubscribed. And that means that we can basically send data back to the central unit in idle times, such as when the vibrator's moving up, or when it's doing a detour, or in between salvos if you're shooting on dynamite. We also have a thing called data safe, where basically we're able to recover the data after a line break. So if a WRU is disconnected, it continues to record the data and then sends it back to the central unit as soon as the wireless network is healed. So the upshot of it is there's no loss of data due to line breaks, and the alternative is to just skip heal over a missing station and record a dead trace at that station for that record. So the conclusion is that the real-time system 2 delivers robust, reliable, and self-sustaining RF networks. So let's have a look at some examples of deployments of the system over varied terrain. So these are shots out in Oklahoma. This is a very complex urban job we did back in 2011 in Dallas-Fort Worth. And it was our first use of discontinuous infill and complex overlay patches. And in this, we had a total spread distance that exceeded 7 miles. Within this particular survey, road crossings and traffic were not a problem. We were able to put our backhaul masts in the central reservations on streets and in people's back gardens. So it worked well. And this was with our first generation system, the RT System 1000. And it was a side-by-side shoot with an RSR. And as you can see and would expect, the data is really very comparable. We did another side-by-side survey last year with a Seismic 428 in Poland with Geophysica Krakow. And we had 25-meter group intervals, 440 active channels with 2 millisecond sample rate, vibrator source with a 32-second sweep and 8-second listen. The terrain was really quite challenging with hills, forests, very deep snow, and extremely cold temperatures below -40 at times. This is an example of the kind of terrain. As you can see, lots of snow, plenty of forest, and fairly rough terrain. That's an example of one of our field records. That's a brute stack from the Seismic 428, and that's the brute stack from our system. And it's, as you'd expect, they're very similar. In Wyoming, we did a standalone job, a 220-kilometer 2D, 1,400 channels, of which up to 717 were live. This was a mixture of vibrosize and dynamite. And again, very difficult terrain with very deep snow, high winds, low temperatures, and an absolute mess from the permitting point of view. And it's fair to say that the crew were extremely relieved not to have to carry lots of cable through the kind of snow depths that they had. And the production actually exceeded their expectations. So these are just some snaps from the crew. As you can see, there was fairly significant snow there. So, but the system worked regardless. That's a brute stack from the survey. Excellent data quality. These are some projects in Colombia. The system worked very well in these heavily forested and extremely sharp relief. You can maybe see here, you can see that there's also, I think it's a 408 system in here that we were working side by side. Some poor person had to unreel a cable through all of this stuff. So it's not just the nicest terrain to have to work in with a cabled system. Also within the passive and frac monitoring market, we've done a lot of work around wellheads. So this is a shot from some distance away, and then if we come in a little bit further, you can see we've actually got both our RT System 2 and the Seismic 408 shooting side by side. You can see we have no cables around ours. The 408 has a nice big cable running right across the wellhead site. Again, from an HSE perspective, that's really quite undesirable. So that's why Microseismic are so enthusiastic about our system, because it doesn't have the cables, yet it can still get the data back for them in real time. So I just put this in really as much for a laugh as anything, because I couldn't quite believe how they'd strapped these geophones to the wellhead. So the system's ideal for frac monitoring, be it surface microseismic or shallow buried arrays. For shallow buried arrays, cables are impractical, and nodes require frequent visits, manual downloads of data, and also they have power management issues. So our system's been effectively deployed on a lot of frac monitoring projects, and it supports full continuous recording, and we've proven that it can produce records that are days long, and it does that in real time with ultra low power consumption. So we're repackaging the system at the moment for the shallow buried array market with a system we call Hercules. And the idea is to scale the RT System 2 from group intervals that might be 50 meters in conventional seismic to 1,000 meters. So the spread dimensions might be from tens of square miles to hundreds of square miles. So Our system will be able to give full spread management and monitoring. Data recording is decoupled from the data transmission, so that means the data is buffered in the local memory, so the telemetry is drained asynchronously. So if there's a break in transmission, it really isn't an issue. There's zero data loss. So we've got a high capacity local memory, a flash memory, that's added to this Hercules system to enable days worth of data if required to be stored. So we're basically going to be delivering two new systems. One is the Hercules Permanent, and one is as a redeployable system. So basically the Hercules Permanent system is based on 4 to 12 channels in one enclosure with a large flash memory. That will also have substantial local power management capabilities from wind and solar generators, as well as other energy scavenging devices. The redeployable device will be focused more on a days to weeks deployment time, and that will be 4 channels with a modified wireless remote unit enclosure. So it'll have slightly larger batteries to just cater for a longer life. So to summarize, the limitations of cable systems are well understood, and we believe they're being further exacerbated by ever-increasing channel count deployments. Nodal systems overcome many of these limitations of cable systems, but they do introduce limitations that cable systems don't have. So we deem that to be an undesirable effect. Radio-based systems, on the other hand, offer the best potential for a cable-free world, but several important challenges have to be overcome. One key challenge: the radio networks must not trade the RF limitations for the limitations of cables. And wireless seismics introduced the real-time wireless system that's delivered and has been proven to be efficient, reliable, robust, and self-sustaining, that answers that main challenge. So the system's been deployed in a variety of environments since 2011, and I think we can comfortably say that the system's demonstrated itself to be a real-time wireless system that is now very commercially viable and competitive. So the system this year, as I said earlier, was proven to be capable of 10,000 channels working in real time. And our challenge now, and this is something we're working on very hard, is to scale the system up from 10,000 channels to multiple tens of thousands. And that's one of the major focuses of the company. I'd just like to conclude by thanking our investors, Chesapeake Energy and Energy Ventures of Norway. If you need more information, you can contact me. That's my email address. And we have our standard fixallinfo@wirelessseismic.com. And I'll just leave you with this small comment at the end. Thank you very much indeed.
The slide pack is okay to go on the internet?
Oh, maybe modify it.
Yeah, okay. Okay, don't sit down. You need to answer questions. That's right. I notice Bob Heath has left the room for an emergency call, so maybe there are no questions from him. Does anybody have any questions? Please, Mike. No. Up front. Sorry.
What are the terrain limitations? I'm thinking about, what about dense jungle or mangrove? Have you considered any of those areas?
Yep. Do I need to go up here?
Yeah, please do. Sorry, I made a mistake before.
Yeah, the system is obviously affected by vegetation, isn't it? There's no question about that. But it's perhaps related to the receiver interval. So because we're not trying to send data over a very long distance, the effects of radio transmission are mitigated to an extent. But we can also, if you are having trouble, if you've got a 50-meter group interval, and for some reason you've got extremely thick vegetation or a very rapid change in relief, we can put a repeater in there. So there are always workarounds.
Okay. Yep. Terry, please.
Tom Martin. Just 2 quick questions. Firstly, on losses, looking at the projects overseas, did you experience losses in terms of theft, and what's the sort of the financial impact of that? The last project I was involved in was a desert project, and you know, the amount of loss of equipment and buried equipment is obviously, you know, I would imagine the price of the unit is significant. But the second one was also, what licensing issues did you encounter with trying to get this technology into countries that perhaps have a more restrictive regime on things that they don't understand, perhaps?
Well, I'll answer the first question first. In terms of theft, we haven't had issues with units going missing, but that's perhaps more luck than anything else, because I know that it is an issue, and it's something we're addressing through putting some kind of tracker system on, because there is a GPS in the unit. So the great thing, though, about our system is that because it's a real-time system, you're not losing your data. And that is not nearly as significant as, for example, losing a Unite box where you've got a month of data. If somebody comes and takes 5 consecutive boxes away, that's a very significant financial hit that you're going to have to take, much greater, I believe, than actually the capital loss of the system. So we're looking at ways to mitigate the theft. It's a question everybody asks, and it's a real issue. But it's an issue for any system, be it a cabled system or a wireless system. In terms of the in terms of the licensing issues for the radio, 2.4 gigahertz, that's Wi-Fi frequency. So most places that we've been to, there is not an issue with the 2.4 gigahertz. There is more of an issue with the 5.8, and we've discovered one instance where we're going to have to dig a little bit further to get clearance. We will get the clearance, but it's just taken more time than we thought, and that's into Russia. They're a bit funny about the 5.8 for some reason, but there were no issues associated with the 2.4 gigahertz.
So just to follow up, just on that, working in North Africa, if every single unit is a GPS, one of the problems we found on the project was the very backward-leaning approach to the control of GPS, in that, you know, the concept of putting GPS out on its own without an armed guard, I think, would be challenging for the local authorities. But no, so you haven't encountered any problems with GPS
No.
licensing, have you?
No.
Okay, anybody else? Yeah.
You see, now
Very robust.
yeah, no, yeah.
Yeah.
Well, that's actually very interesting that you do that, because Mr. Jack was saying earlier he thought this unit was far too heavy. We've engineered it specially so as it doesn't knock over, and that's why it's heavy based.
Yeah.
So that's a very thank you for doing that on cue, David. Yeah.
I'll take my fee later. Thank you. Bob.
Right, thank you. When the unit has been activated, is it then consuming the full amount of current that it takes, or is it in a kind of standby mode and then it powers up when a signal comes through in order to extend the battery life?
Yeah, we always try and decrease the level of activity and therefore power consumption within the unit. So once it deploys, obviously it's using maximum power because it's got to shout out to try and find out where it is. Once it's actually on the line, it will essentially go to sleep until it's woken up by a command from the central. But we're able to do that because we're constantly in contact with the central unit, because it's a real-time system. So that further increases our power, or improves our power budget.
Please.
Hugh Abbott, Marathon. How do the costs compare of this system with the more standard cable system per square kilometre?
Well, it's, you know, we're just humble manufacturers of seismic equipment. But interestingly, one of our customers, Dawson, they told us informally that they were on one of their crews, which is a 3D capable crew doing a relatively small patch 3Ds. They need 40% less people on the crew compared to a conventional system.
Okay. Yeah, Jeff.
Coupling, I presume there's a geophone sitting inside that box there. How does one ensure that there's the coupling between them?
No, there's only one connector on here, and that's a standard KCK connector, so it's an external geophone, or hydrophone, or whatever you want. They can have an array, single geophone, whatever.
Okay, I suppose the next step actually is to combine the video idea that I had with UAVs, and this thing will actually land itself in a few years.
Well, that's the exact idea.
Okay, thank you very much, John.